Today we are going to discuss Edexcel IAL Chemistry Unit 2, May 2019, Part 2. In our last video, we have discussed the Part 1 of this paper. Today we are going to discuss the Section B of this. So let's start. Section B. Iodine can be extracted from seaweed. The seaweed is heated strongly to burn off the organic matter. The resultant ash is boiled in water to dissolve the iodide ions and the mixture is filtered. Acidified hydrogen peroxide is added to the filtrate. A redox reaction takes place with iodine and water as the only products. Now, this is a method of extraction of iodine from seaweed that they basically heat the seaweed to kill all its organic matter, and then the ashes dissolve in water to get the iodide ions, and then in that iodide ions solution, basically they add potassium hydrogen peroxide and acid, and under acidic condition hydrogen peroxide acts as an oxidizing agent and it oxidizes iodine and produces iodine. Hydrogen peroxide itself gets reduced and water will be produced. So the half equation is of oxidation as well as reduction. The iodide ion, they get oxidized, lose electrons and form iodine in the presence of acid. Hydrogen peroxide will gain electrons to form water, and this process is reduction. Use your answer A1 to write the overall equation for this redox reaction. Now the overall equation for this redox reaction includes the equation of both oxidation as well as reduction. If we add both these equations, then here you can see that the iodide ions gets oxidized and hydrogen peroxide is reduced. So overall, this is a redox reaction. Now the iodine is separated from the aqueous solution using solvent extraction. The aqueous solution is mixed with cyclohexane in a separating funnel, forming two layers. The mixture is then shaken gently and left until the layers separate. Most of the iodine dissolve in cyclohexane layer. State the color of each layer after separation. The aqueous layer will be of pale yellow, and the cyclohexane layer, where most of the iodine gets dissolved, becomes pink and purple. Now explain why is iodine is soluble in cyclohexane but only slightly soluble in water. Cyclohexane and iodine form learning forces between molecules. Hydrogen bonds between water molecules are stronger than learning forces. So the iodine is just soluble in water. Due to the presence of hydrogen bond in water. Now the last part of this question 19 is the cyclohexane layer is then removed from the separating funnel and dried. Identify by the name and formulas to the dry agent. You can write any drying agent which you know, like magnesium sulfate or sodium sulfate, endocrine agent, anhydrous sodium sulfate or magnesium sulfate, or even if write the silica gel, it's also fine. Moving on to the next question, that is question number 10. The question is about compounds containing group 2 elements. Hydrated magnesium nitrate has a formula MgNO32XH2O. A student does an experiment to determine the value of XL, leaving 2.15 grams of hydrated magnesium nitrate for 7 hours in amount above. After this time, the solid remaining in a mass of 2.97 grams. So, what happened? Dehydrated magnesium nitrate, which has a water crystallization, has a mass of 5.12 grams. When it is kept in an oven to remove the water, the anhydrous solid which remains after 7 hours has a mass of 2.97 grams. So the 2.97 grams is the mass of anhydrous magnesium nitrate. So if you want to get the mass of water, you need to subtract 2.97 from 5.12 grams. Now question in part 1, state why the student used a warm oven to remove the water from the hydrated solution rather than direct heating with a pulsar. Because the direct heating can decompose the magnesium nitrate. So obviously it's not recommended. So to avoid the decomposition of magnesium nitrate, now use the data obtained by the student to calculate the value of X. Now you have the magnesium nitrate crystal and you need to find the value of X. Now you know the mass of magnesium nitrate, which is the mass of dehydrated magnesium nitrate, and it is 2.97 grams. The mass of water can be calculated by subtracting anhydrous magnesium nitrate from magnesium nitrate crystals. So we can get the mass of water, which is 2.15 grams. So we divide the mass. In the next step, we divide the mass, the molar mass. The molar mass of magnesium nitrate is 148.3. The molar mass of water is 18. Now you get a ratio. Now you divide both the values with the value which is smaller of these. And as you know, 10.02 is a smaller value. So divide both with 0.02 and you will get a ratio. It's 1:6. So now the value of X is 6. Second part, magnesium carbonate is a white solid used as an additive in foods. Explain in terms of energy changes why magnesium carbonate is insoluble in water. Basically, magnesium carbonate has a strong force of attraction between magnesium and carbonate ions. So a large amount of energy is required to break the acidic bonds which is present in ionic lattice of magnesium carbonate. And the energy which is released during the hydration of ions is smaller as compared to the energy which is required to break the ionic lattice of magnesium carbonate. So basically, because of this reason, magnesium carbonate is insoluble in water. So you can write the reason, because this is 2 marks to 1 mark. is for that larger amount of energy required to break ionic bonds in lattice of magnesium carbonate and smaller amount of energy released during hydration of ions when ions form bonds to water. As you know, that breakdown of lattice requires energy. It's an endothermic process where as hydration releases energy. It's an exothermic process. Now the next question is related to the Hess law. The Hess law cycle and data to calculate the energy enthalpy change for the thermal decomposition of magnesium carbonate. Now look at the equation. We have given you the equation of the decomposition of magnesium carbonate, and we have also given you the equation of formation of magnesium oxide by reaction of magnesium and oxygen, and the carbon dioxide by the reaction of carbon and oxygen. So basically, here there is a formation of magnesium oxide and carbon dioxide from magnesium, carbon, and oxygen, and the decomposition of magnesium carbonate into magnesium oxide and carbon dioxide. The values which are given here are all the values of enthalpy change of formation, and we need the value of enthalpy change of decomposition. So we use this value if the sign will become positive. First of all, because we need to calculate the enthalpy change for the thermal decomposition of calcium carbonate, so we will take the equation for the thermal decomposition of calcium carbonate, magnesium carbonate, and that is magnesium carbonate from magnesium oxide and carbon dioxide. And the value of delta H is 1096. This line becomes changed because for the formation the value is negative 1096 and for decomposition it's positive 1096 kilojoules per mole. Now you have the first equation. Now the second equation is the equation of formation of magnesium oxide and carbon dioxide. So basically you have two equations, one of the formation of magnesium oxide and the other is the formation of magnesium carbon dioxide. If you combine both the equations, then or add both the equations, then it's magnesium plus carbon plus oxygen is magnesium oxide plus carbon dioxide. And how can you calculate the delta H value of this equation? The delta H value is calculated by adding the value of the enthalpy change of formation of magnesium oxide and the enthalpy change of formation of carbon dioxide. So it's basically minus 394 will be added to the formation of magnesium oxide, reading that is minus 602. So the value of delta H when we combine the formation of magnesium oxide with carbon dioxide, so the value will be negative 996 kilojoules per mole. So now we have two equations. One is the decomposition of magnesium carbonate and the other is the formation of magnesium oxide and carbon dioxide. Now, to find the enthalpy change for the thermal decomposition of magnesium carbonate, you will add these two equations. So you can have these two equations as there as well as their enthalpy change factors. So delta H is equal to 1096. That will be added to minus 996. So the value of delta H is positive 100 kilojoules per mole. So the positive sign indicates that the reaction is endothermic. Now, next question. Explain the trending thermal stability of group 2 carbonates. Now, group 2 carbonates thermal stability. There's a pattern of group 2 thermal carbonates thermal stability. That the group 2 carbonates thermal stability increases as you go down the group. So you need to remember this trend. It increases as you go down the group. And why this happens? Because as you go down the group, the size of metal ion increases, charge density of ion decreases, so the metal becomes, or the metal is less polarizing. As you know, according to the Fajan rule, the metal ion, if the metal ion is solid, it has more polarizing power. It can polarize an ion more strongly. So the larger the size of the metal ion, the less the polarizing power. So the electron cloud of the anion less distorted, less polarized, and as a result, more energy needed to break down or to break covalent carbonates. Now, next question number 21. The halogen alkene 1-chlorobutane reacts under suitable conditions with potassium hydroxide to form alcohol butanol. Name a suitable solvent for the potassium hydroxide in this reaction. The same reaction can happen in two conditions. So, in this reaction, as it is forming alcohol, so the conditions used is that the solvent will be water. And potassium hydroxide reacts with 1-chlorobutane in the presence of water in aqueous condition to form butane balloon, that is an alcohol. Now, draw the mechanism of this reaction, use curly arrows, and show relevant dipoles and low poles. So all these things contain marks, 1 mark, 1 mark, and 1 mark. So you need to show all these. State the type and mechanism of this reaction. So which type of reaction is this? Basically, in this reaction, chlorobutane will be converted to butane 1-ol. So halogen will be replaced by OH group. So it's basically substitution. And when potassium hydroxide reacts in the presence of water, so what will happen? That the lone pair present on the oxygen acts as a nucleophile, because when the bond between carbon and chlorine will break down, both the electrons will be taken by the chlorine and the carbon will become carbon positive. So this carbon positive will be attracted by the lone pair of electrons which are present on the oxygen atoms. So oxygen acts as a nucleophile basically. So this reaction is nucleophilic substitution. Now we need to show its mechanism. Now we have 1 chlorobutane. This is butane where the chlorine is attached to the first carbon. Butane is having 4 carbons and 1 chlorobutane means chlorine is attached to the first carbon. So what happens when the bond between carbon and chlorine will break? Both the electrons will be taken by the chlorine atom because this is heterolytic fission. As a result, it gets a partial negative charge, carbon gets a partial positive charge. And on this partial positive carbon, the OH will attack. OH right here acts as a nucleophile because it has a lone pair of electron having a negative charge, so it will be attracted towards the nucleus. So as a result, substitution of reaction will happen, and this is called nucleophilic substitution, and OH ion acts as a nucleophile here. So the OH comes in place of chlorine, chloride will form. So here this question is of 3 marks, so you need to show the Cartier arrows here, and you know the direction of arrow should be from bond to atom. The atom which is taking both the electrons, it should not be from atom to atom, it should be from bond to atom. And you must show the relevant dipoles because these carry 1 marks, and the lone pair of oxygen is very important. You must show this lone pair. This carries 1 marks. So please be careful when attempting this question. The second part, a student carried out the reaction. After separation and purification, the mass of butane 1-ol formed was 12.1 grams. When 1 mole of chlorobutane react with potassium hydroxide in the presence of water, it formed butane 1-ol. And the mass of butane 1-ol which is formed is 12.1 grams. The yield of this reaction is 64%. It shows that if we are using 100% of chlorobutane, only 64% is the reaction yield. So first we need to find out the number of moles of butane 1-ol which are formed. So how we can find out that. We have the mass of butane 1-ol. We have the yield of reaction. So this mass of butane 1-ol is basically the actual mass. But how we can calculate the number of moles? For that we need the theoretical mass. So how to calculate the theoretical mass? By using the formula for the reaction yield. So in the first step, we calculate the theoretical mass of butane 1-ol, and for that we will use the formula of percentage yield, that is the actual mass over theoretical mass into 100. So the actual mass which is produced is 12.1. We need to find the theoretical mass. We have the percentage yield, that is 64. So through this formula we can find the theoretical mass, and that is 18.9 grams. Now through the mass you need to calculate the number of moles of butane 1-ol. So in the second step you will calculate the moles of butane 1-ol, and for that you need the mass and the molar mass. You has the mass 18.9 and the molar mass of butane 1 mole is equal to so it's carbon 12 into 4 plus oxygen 1 into 10 plus hydrogen 1 into 10 plus oxygen 16. So the molar mass of butane 1-ol is 74 grams per mole. Now we have the molar mass of butane 1-ol. So we can find the number of moles. The moles is equal to mass over molar mass. We have the mass 18.9 grams. We have the molar mass 74 grams per mole. So the moles are 0.55 moles. So the moles of butane 1-ol are 0.255. Now, you know that the ratio between the moles of butane 1-ol and 1-chlorobutane is to 1 ratio 1, as 1 mole of 1-chlorobutane forms 1 mole of butane 1-ol. So the moles will remain the same. The moles of chlorobutane will also be 0.255 moles. Through moles, we can calculate the mass of 1-chlorobutane. Mass is equal to moles into molar mass. We have moles of chlorobutane and the molar mass of chlorobutane is 92.5. So you can calculate the mass, that is 23.6 grams. You can find the molar mass of 1 chlorobutane. So basically that is 92.5. Now you have the mass of 1 chlorobutane, and if you look at the question, they have asked about the volume of 1 chlorobutane that was used in this reaction. And in the question, they have also given us the density of 1 chlorobutane. So we have the mass of 1 chlorobutane, we have this density, so we can easily find the volume. So how can we calculate the volume of 1 chlorobutane? Volume is equal to mass over density. So it's 23.6 divided by 0.886. So the volume will be 26.7 centimeter cube. So this is the volume of 1 chlorobutane. I hope this is clear to you. Now move on to the next question. Question number 22. An alcohol Y has a structure shown. Describe a chemical test and its positive result for the alcohol functional group in Y. You know, we have different tests for the identification of alcohols. One very common test is to add phosphorus pentachloride, and as a result, the misty fumes form. So this is the chemical test, and this is of 2 marks. So 1 mark is for the reagent and 1 mark is for the result. Now, part B. Y reacts with concentrated phosphoric acid to form 4 isomers with molecular formula C10H18. Draw the skeletal formula of the 4 isomers formed in this reaction. Now, first look at the formula. It's C10H18. Basically, it's an alkene, but the number of hydrogen is not 20, it's 18. So it means it is cycloalkene because they have less hydrogen than normal alkenes, 2 less hydrogen. So it means the structure must be a cyclic structure, and that must have 10 carbons. So you can draw different isomers, like one with 6 carbon, and there must be 1 double bond. So this can be 1 isomer. The second isomer can be 6 carbon, seven, 8, 9, 10. 10 carbons, and it has a double bond. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. Now 1, 2, 3, 4, 5, 6. We can see the position of double bond is different in all the 4 isomers. Now move on to next question. Describe by referring to the wave number in bonds how the infrared spectra of the isomers differ from the infrared spectrum of the alcohol Y. Alcohol Y. The isomers are formed as a result of the reaction of alcohol Y, and the isomers are basically alkenes. So if we use infrared spectrum to differentiate between these two, what will happen? In the reactant, because the reactant is alcohol, so you will find a peak at 3750 till due to the presence of OH bond, hydrogen, oxygen hydrogen bond present in alcohol, which is present in reactant. You need to use a data booklet for this. The peak at 1000 till 1300 due to carbon oxygen bond present in reactant because it is an alcohol. So the carbon, oxygen and hydrogen, all bonds are present. So the value of carbon oxygen bond is the peak will be this. Now in the products, because products are alkanes, so peak will appear at, and that will be due to carbon-carbon double bond present in products, because products are alkenes, and this carbon-carbon double bond is absent in reactants, so these peaks can differentiate between reactants and products. Now part C, an isomer of Y, citronellol, has its systemic name 3,7-dimethyl-oct-6-N1-ol. Draw the structure of citronellol. Okay, so because they have given you the systematic name, so now it's not difficult to draw this structure. Okay, so it shows that it has dimethyl. It means two methyl group. One is at third carbon and one is at seventh carbon. It has 6 carbon chain, 8 carbon chain octa, and having a double bond at 6 carbon, and on first carbon there is an alcohol. So on the first carbon there must be an OH group. Okay. On the third carbon there should be a methyl group. On the seventh carbon there should be a methyl group. And on sixth carbon there should be carbon-carbon double bond. Okay, now let's draw the structure. First carbon, OH group is attached. On third carbon, a methyl branch is attached. On sixth carbon, a double bond is present. And on seventh carbon, a